Although I don't know about Martin if you were like technically working with BMW at the time that you started, but yeah. Anyway, awesome. So not sure if we need an introduction to flaky tests, but here's the 30-second version just in case. When we make changes to our code, we run some tests to determine whether or not those changes introduced any bugs. And oops, right. If our test passes, we say that's great. If our test fails, we probably can also still say that that's great because, you know, at least we found the bug. But what becomes kind of challenging are these flaky tests where we see that the test failed, and then we say, great, we found a bug, let's go and debug it. And then you run the test again, and the test passes, and you're like, well, what the heck is happening here? Did I introduce a bug, or is this test flaky? Yes. So flaky tests are these tests that can pass or fail non-deterministically. A considerable amount of prior work, including my own, focused on some really specific kinds of flaky tests. Like, for example, flaky tests that are flaky due to this order dependency. These are tests that can fail when run in different orders. Some of the past work in this area has included approaches to maybe like either isolate tests to prevent those dependencies, or to efficiently schedule those tests to avoid those dependencies. But we've been looking at this problem of flakiness more broadly. So while there can be many different underlying root causes of test flakiness, kind of shown here in this pie chart, this pie chart is from a great piece of work now. I don't know. I think that this paper should receive FSC 2024 N-10 Best Impact Paper Award. This was FSC 2014, Luo et al., a survey of flaky tests in open source projects. They found flaky tests in projects, they hand analyzed them to determine what the underlying root cause is. Others have repeated this work since then on newer data sets in different projects. And the overall distribution tends to remain kind of the same, some things kind of change. Overwhelming root cause of flakiness in these projects is categorized here as async weight, that big yellow one on the right. These are tests that have some asynchronous aspects and just lack proper synchronization. And designing asynchronous code for testability really requires a lot of forethought. The few common fixes we've seen, like one is you might add retries, maybe with a timeout, to say, do something in the background, wait for it to happen. If it doesn't happen in time, maybe just try again until some certain timeout. And the reason why these are so frustrating is there are a lot of maybe infrastructure related causes that are totally unrelated to your code or your changes that could affect timing. You're like, well, you know, today I'm running my tests and it keeps failing. Maybe the reason why it keeps failing is due to this timeout, and it's going to keep timing out even if I retry it because the build cluster that we're running on is super busy and overloaded because someone thought it would be a good idea to run a lot of tests in parallel. Other fixes that we've seen, frankly, are just to like outright remove assertions and just kind of like avoid testing these kinds of behaviors. Reworking these tests to eliminate flakiness is like a really big challenge. I think maybe a growing perspective that we discussed at the Flaky Test workshop at ICSI is that really saying that something is a flaky test is another way of kind of papering over and saying like, we knew that we could have written the test better, but it would have taken a lot of effort, and that wasn't that high on our priority queue. So we can just, rather than even put that on a technical debt roster, we'll just say that's a flaky test and we can't solve it. So kind of the goal of this work was to come up with an approach where we can automatically detect these kinds of problematic tests and come up with something that can reduce the failure rate of these tests, ideally without requiring some kind of like significant developer effort. So here's an example of one of these async weight flaky tests. This test is taken from an open source Java project called Java WebSocket. And this test is a regression test that's supposed to confirm that when a WebSocket is closed, the server transitions into this is closing state. And then eventually it closes. So this is a flaky test, and it will fail intermittently because this close method is asynchronous. The socket doesn't enter the is closing state immediately. So we have this assertion below it that after calling close, it checks to see is closing true. Sometimes when the test runs, the server reaches the is closing state before hitting the assertion, and sometimes it doesn't. We can see that one there. This is particularly interesting one also from like, what can developers do about it, and how do we design tests for code for testability, especially when there's asynchronous stuff involved? Because you can see that, sorry, window management is tough. You can see that someone did have the forethought to realize that close is asynchronous and is closed on the bottom line, that assertion. That one, we want to have some kind of waiting to make sure that the close actually happens. This countdown latch 0, the code is off screen, is like something that's going to do some synchronization on that. They synchronized on that one, but they didn't synchronize for close. So these are kind of tricky things to solve. So our key insight is that these async wait tests are also really likely to be highly affected by timing and resource availability. So for example, if we're competing for CPU scheduling, we're running a lot of tests in parallel on a machine because, you know, keep hearing we've got lots more developers, we've got lots more tests, we've got to run more tests. You know, kind of actually the inspiration for this project came from one of my students who had done an internship at Uber. No one here works at Uber, right? Great. Where, you know, they had this problem, and in the kind of relatively early days there, like, let's just fix this. We can get, you know, improve latency much better. We've got like our build server with 100 cores. So, you know, we can just run, you know, everything in parallel without any kinds of bounds. And then all of a sudden you end up realizing that some tests that normally, sometimes they get 4 CPUs, other times they get 2 CPUs, sometimes they get a fraction of a CPU. And these things that are timing dependent, like shockingly, when they don't get CPU time, they kind of behave funny. So in this study, we aim to detect what we call resource-affected flaky tests, or RAFT. We define a test as RAFT if its failure rate is statistically significantly higher when run in a resource-constrained environment than in a baseline one. And this project, as it turned out, in addition to becoming this like really big piece of empirical measurement of running a lot of stuff and collecting a lot of data, we also learned a lot about statistics along the way. There's a lot of false signals that you can find when you look at data like this if you don't like use statistical methodologies that are sufficiently rigorous to identify noise. We're studying things that are inherently non-deterministic. We understand that there are going to be kind of like some underlying random noise there. And to actually find things that matter takes more effort. So our study design, we studied open source projects. We started out only studying projects in Java. We submitted that to ISTA. I got a reviewer who said, oh, you only studied stuff in Java. There are other languages out there too. So we also studied projects in JavaScript and Python. And we ran each of those project test suites 300 times in a virtual machine with 4 CPUs and 16 gigabytes of RAM, which we figured to be like a sufficiently reasonable like baseline event. Then we did 300 more repetitions of all of these test suites in all of these different resource-constrained environments. And we had kind of 2 approaches to constrain resources. In one approach, we just like really severely throttled access to CPU, memory, disk, and network throughput, like going down to 1/10 of a CPU, going down to, you know, kilobytes a second of disk I/O, going down to hundreds of megabytes of RAM. We use those resource configurations to explore the pairwise impact of throttling different resources. So for those different combinations of CPU, RAM, disk, and network, like we chose all possible pairs. So we identified tests that could be RAFT under, you know, single resources or under multiple. And then for something that might be a little bit more appropriate in the real world, we also selected 11 configurations that match popular cloud offerings. And if you were going to like go and spin up containers on Amazon ECS Fargate to run your flexible CI stuff on, we picked configurations that match what you could pay for there. So before getting into the study results, I'll walk you through the methodology on one example flaky test, and also kind of hint at some of the different configurations that we explore. So I show on the right the number of failures that we observed when we ran this test using just 12 of those 37 configurations that we tested. So for each configuration, besides the baseline one, we perform a chi-squared test on the difference of proportions of failures between that configuration and the baseline. Super important when you do work like this also is that you also have to account for an increase in the false discovery rate from having multiple statistical tests. So this is the like kind of phenomena where you say like, great, we'll just accept, you know, 5% false positive rate. But then when you do that thing 300 times, if you don't account for compounding the false positive rate, like you just end up full of false positives. So we use the Benjamini-Hochberg procedure to account for that. And then declare a test as RAFT when we see a configuration with a p-value less than 0.05. So in this case, we can see that this test is detected as RAFT in some of these very extreme configurations where the test is allocated just 1/10 of a CPU. Then we also want to try to express the severity of this impact, and we calculate the difference in proportion of the failure rates. So that's comparing from the maximum of 54 out of 300 to this baseline of 14/30. We see an absolute increase of just 13%. We have a lot of data. I'm going to just show a really quick summary of it. There's a preprint on arXiv that has like all of it, and on Zenodo we have like all of the data, including like the JUnit XML Surefire reports and all the stuff. So what these Venn diagrams show is the number of RAFT that we detected in just a subset of the configurations. On the left side, we see these different configurations where we had different things throttled. So how many RAFT we found throttling just CPU, memory, network, disk, and then also those that we found only when we compared throttled multiple of those things. A few quick takeaways. Across all of the configurations, we found 608 flaky tests. 283 of them were confirmed to be RAFT, which is a pretty sizable proportion of those. We found RAFT in about half of the Java projects and about 20% of the Python and JavaScript projects, maybe just kind of representative of the sampling of the projects that we took. We found that CPU availability was the largest single influence on flakiness in these projects, although we also found some RAFT that were sensitive only to memory availability and not CPU availability. Potential like practical importance here, parallelization. You have some fixed amount of resources. You want to run as many tests as you can concurrently. Like maybe this is a good methodology to use to determine kind of like where the sweet spot is going to be for minimizing flakiness while maximizing concurrency. Again, hard to fit all the data into the into the talk, but just kind of giving a taste of more of the kinds of statistics that we computed. This bar graph shows the difference in failure rates for each of the resource-affected flaky tests. A quick interpretation of this, we're looking at these difference in failure rates, so like how much flakier was it in these constrained configurations versus the baseline. The dark green represents the number of tests with a difference in failure rate of up to 10%. So the absolute increase in failure rate was less than 10%. So as you can see from squinting at this, despite the size of the screen, squint test should hopefully work. It's the case for the majority of the RAFT, which indicates that for many of these tests, there's only a small, but nonetheless significant effect on their effect of the failure rate. The color scale goes all the way to red, where you can see that for some of these flaky tests, there's at least a 75% increase in failure rate. And like the other thing that's not shown here is like probably not a shocker. There are some tests that when you constrain their resources, they don't just become flaky, they just always fail. They're like, out of memory, I'm done, right? And it never works. So you know, there's that's going to be another constraint if you want to minimize the resource that you assign to tests, but it's not really affecting what we would say is being flaky because it's just like persistent. Trying to get more into like potentially practical implications. Using this information, it's possible to either minimize or maximize the number of flaky failures per project. So this bar graph shows the number of projects that had the best reliability and price. The dark blue and purple is the best of both per configuration. Not surprising, the best configuration of what gives you the least failures at the least cost it varies a lot by project based on the actual resource requirements for the project's tests. We checked the documentation for each of these projects to see if there were suggestions of minimum resource requirements and found, interestingly, that none of them had them. We began to offer pull requests on these projects, kind of suggesting that some of these minimum resource requirements could be added in a way to help contributors run these projects efficiently and avoid flakiness. We received mostly positive responses thus far, but this is really going to take many open CI systems kind of to a level beyond what is normally configured by end users. For we're using GitHub Actions with like open source projects, we're just going to be getting that 2 CPU, 7.5 GB runner unless we decide to start paying for it. And if you're going to start paying for it, hopefully you're not paying GitHub for it because you're just paying through the teeth for it. Well, we assume probably most developers want to minimize failures. There are also definitely researchers who probably want to maximize failures. And we can find optimal configurations per project for this too. Kind of an interesting side effect is like if you want to study flaky tests and if you want to go out there and find flaky tests, you can do it much more cheaply by using less resources to run your tests. And again, like this kind of varied across project, what was the best, because eventually when you get too low, you just have persistent failures and that's the end of it. Doing this, you can potentially save money. So the left histogram here shows a hypothetical savings rate per project, assuming that these projects were paying for CI, although like to be clear, these are mostly open source projects, like using free CI systems. And assuming that they were using this baseline CI runner, the scale goes from 0 to 100%. It's a histogram. So you can see that there's kind of like a cluster of projects that don't save a lot, but then there would also be kind of a cluster of projects that do save much more. Something that I'm particularly curious in hearing feedback from different industry practitioners is like the extent to which anybody thinks about this, cares about this, or could consider this as a reasonable cost savings, or if it's a cost that simply doesn't matter in terms of how much is being spent on CPU resources. I know for sure today that like at least in the kinds of data center equipment that we have in Northeastern, you know, if you're like, I just need CPUs, they're like, oh yeah, have CPUs, that's fine. And you're like, oh, we need GPUs. And they're like, ooh, get in line. Still, of course, I understand at some scales, you know, you do hit that overall limit of like, we're using all the power in the building. So where we go from here, we found that the easiest way to reduce the impact of these async wait flaky tests is simply to ensure that they have enough resources when running. A lot of other interesting future research directions in this async wait stuff. One might be to consider finding automated refactorings that could reduce flakiness. So once we decide where these async wait flaky tests are and what their causes are, which you could maybe use this kind of throttling approach to find and do some delta debugging, you know, we can automatically generate fixes, try to make that assertion pass. We might also consider trying to help developers repair these problematic assertions by localizing the fault, maybe adding intentional delays before the code that emits the asynchronous event to force the failure to happen deterministically. And overall, just kind of generally interested in future work and flaky tests and resource availability. Tons more data and discussion and artifact available on archive. Really look forward to discussions now, over lunch, and over dinner. Thanks.
Thanks for the presentation. You've talked about minimizing the fail rate in industry projects by setting the right resource limitations. Typically, people argue against rerunning, and I think it applies there as well, that the problem might originate from the system under test and there's actually something going wrong that should be repaired. Did you see anything in your study where the problems come from? Do they come from the system under test and should be leading to failing tests, or is it usually coming from the test infrastructure, test code, test setup?
Yeah, great question. Thank you. So I think that what we saw most commonly was like really this kind of pattern where, like, I guess we could say that the problem is in the test, right? Like the problem is that the test isn't waiting for the thing to be done, and it's assuming that it happens like instantaneously. But it's not really just a problem in the test, right? Because to make the tests that would be more resilient, you also need to make changes in your production code to make it more testable. And then I think like if you tried to take this more broadly, like I assume you end up having like kind of some bickering going on between like, well, this is the appropriate way to design the system, or like, but then it's not testable, and finger pointing. I think that the I'd be curious to hear more about, in industrial settings, the extent to which resource expectations for the system under test are sufficiently communicated and then enforced at testing time. Like, is this a problem or is this kind of solved? Great.
I would say it's a problem.
Yeah. I mean,
Is this a problem for you guys? Yeah, it's a problem. Okay. So yes.
Like, and do people care? Like, are the costs of CI infrastructure sufficient to say like, yes? Yeah. Okay. Cool. Yeah. Stan.
I don't know. Maybe I'm reading too much into the example that you that you included, but I think that it would be interesting to know, like, to go like a step further and identify bad APIs, because I don't know how common are flaky tests, because like developers just misuse the API, because you cannot see that close is asynchronous. If it was explicitly like typed as asynchronous and then you cannot do anything except await on it, then it might fix. I don't know how many of those issues are just like scattered or concentrated around common but poorly designed APIs.
Yeah, probably both. So I think, especially with these specific examples of like, we have async APIs, we have a TypeScript data set also. And what would be really nice is if there was like a keyword that you could use to decorate your API to say that it was asynchronous, right? And then maybe prevent this kind of issue. That's something that we haven't kind of sliced the data to look at across languages, but would be interesting. Specific to this API, would you like, so this flaky test was fixed. Who would like to guess how this flaky test was fixed?
Somebody say sleep.
I heard sleep. Change the API to improve documentation. I don't know. Ola in the back.
They should have done. I don't think it's change the underlying code to special status to closing synchronously and only do the rest of the things asynchronously.
So
that is, I think, the best suggestion. Yeah. That was, I think, the best suggestion, which is, it seems like even if close is an asynchronous API, the fact that is closing like should be a synchronous operation when close starts. In the interest of time, I'll tell you what the actual fix was. They deleted the assertion is closing. Yes. So it's a mess out there. Yeah. Tim.
Practical question. Okay, so you were talking about family-wise error rate correction early on, which is, I think, actually not just a research question, it's also a practical question on how much data do you really need to collect to identify, because in your distribution plot that you had, most things are like only slightly sensitive to resources, and then some things are like really sensitive to resources. How much data do you really need to collect for those sensitivity levels? And do you need to do like continuous family-wise error rate correction, or can you just like set a single threshold? What's the deal here with significance testing?
A statistics question. Thank you, Tim. So I think like maybe to summarize it, the question is, how do we decide 300 trials, and how do we decide over time, as we continuously do this, how we adjust the values? So yeah. So 300 was something that was decided in 2018 before we had most of these configurations and before we had TypeScript and Python. So it was a number that came out of the air. What we should have done was do a power calculation where we say we want to have this significance level and we want to have this, false positive rate and this false negative rate. and then like this many comparisons, and then like the output of that is like you should do this many trials. So what we're risking here is false negatives, right? So we are missing detecting flaky tests that are RAFT, but like only at a very low level. Well, I can't even say that it's at a very low level though, because I can't, right? Because of the statistics issue there. Yeah, it's hard. I need to consult further statisticians for their details. Yeah, thank you.
Everybody's favorite topic.
Yes.
And I think we're about at time for the presentation section. So I want to thank our presenter and actually thank everybody who presented today. So at this point, I'm going to give us like a 2-minute break and whatever. That's fine. We're going to do in this room in minutes. We'll do I think it's called a panel discussion. In the past, we have done sort of a group discussion that the organizers facilitates. I guess that's me this time on what are big challenges right now going on in industry for CI/CD. So we have an opportunity discussion for what's the biggest challenges right now. We can draw for that discussion on the presentations that we saw today. I think we saw some interesting areas to maybe discuss and what the impact is. So we'll probably spend approximately 30 minutes on the panel discussion, and that will close our workshop for today. And I want to repeat, since we have some different people in the room now, what I said before our snack break, which is that we are going to be going out for dinner as a workshop. If you want your email items to the list that I'm maintaining, I'm going to email out where we will go. We will go someplace that's relatively close to the subway line, the yellow one on maps. The one. So that if you don't have a car, you can get to the dinner location. Just let me know if you'd like to be included, and I will call to make a reservation after the workshop closes. All right. Well, thank you very much. A couple of minutes, and I guess we'll start back up. Actually, I'll give us 5 minutes. We'll start back on by 12 for the panel discussion. Thank you.